Alright, so today we're going to have a look at exercise 1.6 for extension 2. We're looking at the zeros of a polynomial. Now a lot of you in class, we got up to 2C at least, so I'm going to start at 2D. So we have to solve the following for z as a complex number. For z to the power of 4 plus 2z squared plus 1 equals 0. Alright. Here we're going to use a u substitution, so if we let u equal z squared, this is going to be u squared plus 2u plus 1 equals 0. Now that's a perfect square, so this is going to be u plus 1 squared is equal to 0. We square root both sides, we get u is equal to minus 1. Now we know, however, though, that u is equal to z squared. So since u is equal to z squared, then z squared is equal to minus 1. If we square root both sides, we get plus or minus I, and that's the solution there. Okay, number 3, we're asked to solve the equation z cubed plus z squared plus 3z minus 5 equals 0, and we're solving it if z is a complex number. Okay, so what we might do here is we might figure out if there's any solutions to this equation over the real numbers. So we might substitute in 1, so ants cubed plus ants squared plus 3 ants minus 5. Now 1 is a factor, so I'm going to factorize by z minus 1 and do some polynomial division. So z cubed plus z squared plus 3z minus 5. We polynomial divide, we get z squared, and then z cubed minus z squared. Down here we're going to have minus 1 minus minus 1, so 2z squared plus 3z. We're going to have plus 2z. And then we've got 2z squared minus 2z, so we're going to have 5z minus 5, so plus 5z minus 5 is 0. So part A over the set of real numbers is going to be z minus 1, and then z squared plus 2z plus 5. So that's part A. Now part B, we're going to have a look at factorising z squared plus 2z plus 5. Now I'm going to use the quadratic formula for that. So z is going to equal minus 2 plus or minus the square root of 2 squared minus 4 times 5, which is minus 16. So minus 16 on 2. So minus 2 plus or minus 4i on 2, which is minus 1, plus or minus 2i. Now we're asked to solve, so we don't need to just factorize this. In fact, I think I misread part A. We're asked to solve. So if that equals 0, the only solution is z is 1. And over here now we've got z is minus 1 plus or minus 2i. So therefore the solutions are 1 and minus 1 plus or minus 2i. And that does make sense. Using the fundamental theorem of algebra, we were expecting 3 answers. Right, I'm going to skip down to question 7 now. So we're solving z to the power of 4 plus 2z cubed plus z squared minus 4 equals 0. Alright, what we might do is we're going to figure out whether there is any solution. So let's substitute in 1, for example. To the power of 4 plus 2 ants cubed plus ants squared minus 4. 1 is a solution, so let's polynomial divide by 1. So we get z to the power of 4 plus 2z cubed plus z squared minus 4 equals 0. Oh, not equals 0. I'm going to leave that. We're just polynomial dividing. Minus 4. So we're going to have z cubed. Now I have missed actually in my polynomial division. We have to make sure we put a plus 0z there. So z cubed, and then we've got z to the power of 4 minus z cubed. So we're going to have 3z squared plus 3z cubed, sorry, plus z squared. So we've got a plus 3z here. We might move that. We need a 3z squared there. So 3z cubed minus 3z squared is 4z squared. We've got plus 0z. So plus 4z. We've got 4z squared minus 4z is 4z. Bring down the minus 4. Put a plus 4 here. And 4z minus 4. So therefore we've got z minus 1. Z cubed plus 3z squared plus 4z plus 4 equals 0. Now this is a cubic, so we can't yet use the quadratic formula. Let's have a go at finding another factor. I might try, let's try 2 first up. Z cubed plus 3n squared plus 4n plus 4. Now let's try minus 2. There we go, minus 2. So z plus 2 we're going to divide by now. Z cubed plus 3z squared plus 4z plus 4. Now if you do that, I might just do all the steps in one. It's okay if you can't do this quickly, but it's going to be what, z squared plus z plus 2. That will be the answer there. So z minus 1, z plus 2, z squared plus z plus 2 equals 0. So we might use the quadratic formula to solve that quadratic. So z is equal to minus 1 plus or minus 1 squared minus 4 times 2. So that's root 7 minus 7, so root 7i on 2. So therefore our solutions are z equals 1 minus 2 or minus 1 plus or minus root 7i on 2. Question number 8. Now we're solving if z is a real number, so we don't want any complex solutions here. So we've got 3z cubed minus 4z squared minus 13z minus 6 equals 0. So 1 is a factor, so let's divide by z plus 1. So we're going to go 3z cubed minus 4z squared minus 13z minus 6. Now again, if you do that, you're going to get 3z squared minus 7z minus 6. And that will give us, okay, it's, I don't know what happened there, there's a z there. We're going to have z plus 1, 3z squared minus 7z minus 6 equals 0. We might use the quadratic formula for that middle thing. So z plus or minus 7 plus or minus 3 squared minus 4 times minus 6 is 4 times 3 times minus 6 is 81. Root that, we get 9. So plus or minus 9 on 2 times 3 is 6. So 7 plus 9 on 6 is 8 on 3. Wait, no, it's not. Something's gone wrong. We get, 7 plus 9 on 6 is 8 on 3, or minus 1 on 3. So therefore our solutions are z is equal to minus 1, 8 on 3, or minus 1 on 3. It's a bit different from what the answers had, so I might just check if I've done something wrong. It'd be 7 squared minus 4 times 3. Oh, no, I have done something wrong. Ignore me. So z is equal to 7 plus or minus. The discriminant is going to be 121. We square root that, we get 11 on 2. So 7 plus 11 on 2, we get, not on 2, I keep making silly mistakes, sorry. Over 2 times 3 is 6. So 7 plus 11 on 6 is 3. And 7 minus 11 on 6 is minus 2 on 3. So therefore our solutions are z is minus 1, 3, and minus 2 on 3. We might skip down to question 11 now. So we've got, if z is a complex number, we've got z to the power of 4 plus 4z cubed minus z minus 4 equals 0. So we're trying to solve as if z is a complex number. So again, we're going to see if there are any factors here. So I might substitute in 1. So 1 to the power of 4 plus 4 times 1 cubed minus 1 minus 4. That's 0, so we're going to polynomial divide by z minus 1. We get z to the power of 4. 4z cubed minus z minus 4. Polynomial dividing that, we're going to have z cubed, and then z to the power of 4 minus z cubed is 5z cubed minus z. Up here we're going to have plus 5z squared. And again, you can see I've missed my plus 0z squared, so please don't make that mistake like me. So then we're going to have, so we bring down our plus 0z squared. So then we've got 5z cubed minus 5z squared. So we're going to have 5z squared minus z plus 5z. 5z squared minus 5z is 4z, and then minus 4. Got a plus 4 up here, so 4z minus 4 is 0. So we've got z minus 1, z cubed plus 5z squared plus 5z plus 4. So that's a cubic equation, which means there's going to be 2 more complex solutions. So that means there has to be 1 more real solution. Let's have a go at substituting in some values. I just quickly got minus 4. So minus 4 is a value. So z minus 4. Polynomial divide by z minus 4. So z cubed plus 5z squared plus 5z plus 4. Now if you do that, you get z squared plus z plus 1. So our new factorization is z minus 1, z minus 4, and then z squared plus z plus 1, and that's equal to 0. Now we might use the quadratic formula to solve that. So z is equal to minus 1 plus or minus 1 squared minus 4 times 1 is minus 3, so it's going to be root 3i over 2. So therefore our solutions are z is equal to 1, 4, and minus 1 plus or minus root 3i on 2. Part B. Got z to the power of 6 minus 16z cubed plus 64 equals 0. Okay, this we're going to use a u substitution here. The reason I can do that is because the coefficient of z, or the power of z cubed, we can see that the next thing, z6, is double 3. So whenever you've got the first term is to the power of 6 and then the next term is a cubed, or you've got the first term is to the power of 8 and the next term is to the power of 4, we're going to use a u substitution. So let u equal z cubed. So it's going to be u squared minus 16u plus 64 equals 0. Now that's a perfect square. U minus 8 squared equals 0. So we also know that u is z cubed, so z cubed minus 8 equals 0. And if we take the square root of that, we're going to have z cubed minus 8 equals 0. Now to solve this, we're going to use the factorization of a difference of 2 cubes, which you learnt in your holiday homework I assigned you. So this is going to be z minus 2, and then z squared plus 2z plus 4 equals 0. And then if we use the quadratic formula for the middle, the quadratic, minus 2 plus or minus the square root of 2 squared minus 4 times 4 is minus 12. So minus root 12i on 2, which is minus 2 plus or minus. Root 12 is 2 root 3i on 2. So it's minus 1 plus or minus root 3i. Now, on purpose, I'm going fast because I'm recording a video, so make sure you're pausing as you're writing in your solutions. The only reason I'm going at this speed is because you can pause me. So, therefore the solutions are z is equal to 2 and minus 1 plus or minus root 3i. Alright, let's have a go at 13. We've got find real values of a for which ai is a root of the polynomial equation z to the power of 4 minus 2z cubed plus 7z squared minus 4z plus 10 equals 0. Now we might note that this complex equation, this equation has real coefficients, which means the roots are going to occur in conjugate pairs. However, if we say let this equal to p of z, then p of ai is going to be a solution to this equation. In other words, ai to the power of 4 minus 2 times by ai cubed plus 7 ai squared minus 4 times ai plus 10 equals 0. Now I to the power of 4 is 1. So this is a to the power of 4 minus I squared is minus 1, and I cubed would be minus I, so this is minus 2ai. I squared again is minus 1, so minus 7a squared minus 4ai plus 10 equals 0. Now here we're just going to equate our real and imaginary components. So if we have a look at the imaginary why don't we have a look at maybe the real components. So if we have a go at we might actually look at the imaginary components here. What I've actually have missed out on is this cubed here on the a. There's a cubed there. So if we have a look at our imaginary components, the imaginary components of this is going to be minus 2, or plus 2, that's a plus there, because I cubed is minus I. So 2a cubed minus 4a, that's the imaginary component of this equation. And that has to equal 0. Remember, when we equate real and imaginary components, if this equation is equal to 0, then the real components have to be 0 and the imaginary components have to be 0. Now, if you go about solving that, you're going to get a is equal to plus or minus root 2. And that's the answer there. Number 15. Find the three roots of the equation z cubed minus z squared plus 2 equals 0. Now I'm thinking we might potentially use substitution, maybe not, let's have a think. No, we can't use substitute, this would have to be a 4 to do that, so we might polynomial divide. It looks like, just in my calculator, minus 1 is a factor, so z minus 1, we're going to have z cubed minus z squared plus 0z, I didn't forget that time, plus 2. Now if you do that, you get z squared minus 2z plus 2. So this is z minus 1, z squared minus 2z plus 2 equals 0. Now if we use the quadratic formula to solve that, we get 2 plus or minus 2 squared minus 4 times 2 is minus 4. Square root of minus 4 is 2i over 2, which is 1 plus or minus I. So therefore our solutions are z is 1 or 1 plus or minus I. Part B, we're asked to find the remainder when it's divided by z minus I. So using the remainder theorem, p of I is going to be the remainder. Now p of I is just I cubed minus I squared plus 2, which I believe is 3 minus I. So that would be the remainder there. So again, we did learn this in class, but the remainder theorem and the factor theorem still works for complex numbers. We might skip to 17. Solve the following equations using a calculus method. So this is our multiplicity of roots that we learnt in extension 1. So z to the power of 4 plus 4z cubed plus 5z squared plus 4z plus 4 equals 0. Now we're told that given it has a root of multiplicity 2. So we might differentiate this. So p, if we call this p of z, differentiate it once, p dash of z equals 4z cubed plus 12z squared plus 10z plus 4. Now, if you go about solving that equation, if you do some polynomial division, you're going to get minus 1, minus 2, and minus 4. No, you're not. You're going to get minus 1 and minus 2. Minus 1 and minus 2 are the solutions. Actually, no, you're not. Ignore me. I might just polynomial divide because the answers are not quite helping. So I might just polynomial divide myself. So let's find p of 1. So 4 ants cubed plus 12 ants squared plus 10 ants plus 4. 1 doesn't work. Minus 1 doesn't work. 2 doesn't work. Minus 2 works. So p dash of minus 2 is equal to 0. Now let's find what p of 2 is. So if we put p of 2 into the original equation, we go ants to the power of 4 plus 4 ants cubed plus 5 ants squared plus 4 ants plus 4. Put in minus 2, not 2, I don't know why I said that. So minus 2, p of minus 2 is also 0, so therefore minus 2 is a double root, or is the double root. So what that actually tells us is that p of z, well, we know that 2 is a double root, so z plus 2 squared is a double root. But this is a quartic equation, it's to the power of 4. So there's going to have to be some quadratic equation times by here. Now, this is going to be 1 here. We don't have to bother finding that because we know that the coefficient of the first term, z to the power of 4, is already 1. So we're going to put a 1 here. If it wasn't 1, we would need to put an a here. Or if it was 2, we could put a 2 there and it would also work. In fact, yeah, we would have to put a 2 there. So if we had a 2 here, we'd have to put a 2 there. So if we go about expanding this, so we've got, what have we got? 4. If we have a look potentially at the last term, so the last term, the constant term, is going to be 4 times by, or 2 times 2 times 2, not 2 times 2 times c. 4c is equal to, it has to equal 4 because that's the constant of the original equation. So c is equal to 1. And then we've got to think about what b is equal to. So z plus 2 squared. We figured out c, so this is z squared plus bz plus 1. We figured out c was 1. And if we have a think about what's going to happen here, if we expand this expression here, so this is z squared plus 4z plus 2, that's a z there, and the second one's a 2, times z squared plus bz plus 1. Now if we have a go at expanding this, it's going to be z to the power of 4 plus bz squared plus z squared plus 4z cubed plus 4bz squared plus, that's a 4 there, pardon me, plus 4z plus 4z squared plus 4bz plus 4. Now we're going to have a look at everything. We might have a look at our z squared terms. So we've got a z squared here, a z squared here, and a z squared here. So z squared, or bz squared, plus 4bz squared plus 4z squared. Well, if we take out the z squared is going to be b plus 4b plus 4. And that has to equal the coefficient of z squared in the original equation, which was 5. So this has to equal 5. we can get rid of that z squared there. This has to equal 5. So in other words, 5b plus 4 has to equal 5. Which means b has to equal 1 on 5. I think potentially something's gone wrong here. Let me just have a look at what's gone wrong here. You might want to skip past this part of the video until I get it. I think I've expanded this wrong. Let me have another go. So z to the power of 4 plus z squared bz plus, oh, that's what I've done wrong. Z squared bz is a cubic plus z squared plus 4z cubed plus 4bz squared plus 4z plus 4z squared plus 4bz plus 4. We might just look at the z's, the ones that only have z. So that's that one and that one. So 4z plus 4bz, that has to equal the coefficient of z in the original equation, which is 4. So that means 4, if we take out a factor of z, 4 plus 4b has to equal, the term of z was 4z in the original equation, 4z. Cancel those z's. We've got 4 plus 4b is equal to 4, which means b is equal to 0. So therefore, back to this here, we've got z plus 2, z squared. Now b is 0 plus 1, and that equals 0. So therefore, z is equal to minus 2, or z squared plus 1 is equal to 0, which means z is equal to plus or minus I. Okay, I'm going to skip to 18 now. So I want you to do b without watching my video, so try and figure that out on your own. If z is a complex number, solve z to the power of 4 minus 2z squared plus 9 equals 0. Given that 1 plus 2 root 2i, so we're told that 1 plus 2 root 2i is equal to root 2 plus I squared. Not quite sure how that's going to help us at the moment, but I guess we'll find out. I'm thinking personally we might want to do a u substitution. So let's go, let u equal z squared. So that means u squared minus 2u plus 9 equals 0. That's not going to be the prettiest thing, unfortunately, so let's go use the quadratic formula. U is equal to 2 plus or minus 2 squared minus 4 times by 9 is root 32, or it's minus root 32 on 2, which is equal to 2 plus or minus, now minus root 32 is root 32i on 2, which is 2 plus or minus, now root 32 is 4 root 2, so plus or minus 4 root 2i on 2. Cancelling out that 2, we've got 1 plus or minus 2 root 2i is our solution. But we actually said that was equal to u, but u was z squared. So z squared is equal to 1 plus or minus 2 root 2i. Now, in the question, we're told that 1 plus 2 root 2i is equal to root 2 plus I, all squared. So, let's write that down. 1 plus 2 root 2i is equal to root 2 plus I squared. So, what that means is this is equal to 1 plus or minus, oh, it's not, pardon me. This is equal to root 2 plus or minus I squared, using that identity here. Now, the reason we this clue helps us in the question is because otherwise we would have had to find the square root of that complex number there, which would be quite tricky. So z squared equals that. Now we can just simply square root both sides. So z is going to equal, if we square root, remember we get a plus or minus, so plus or minus root 2 plus or minus I, and that's our answer. I really enjoyed that one. All right, thank you for listening. Hope that makes sense.